Ladies and gentlemen, welcome to the first talk of this session. The speakers today are Dan Cristofaro Gardini and Sobhan Seyfaddini. They are experts in simplistic geometry. Today they will talk about on the algebraic structure of groups of area preserving homeomorphism. Join me to welcome them.
Great. Thank you very much. It's really a great pleasure and a great honor to be here at this ICB at the International Congress of Basic Science. So me and my collaborators, we are grateful to the organizers and also the prize committee for inviting us. It's really a great honor to be here. Okay, so in the schedule it's written that I'm the speaker. So I'm Sobhan Seyfaddini, and I was supposed to be the speaker, but we realized that recently that we have the option of actually giving a joint talk, and we thought that would be fun to, since Dan is here, we thought it would be fun to present the talk. So I'll present some of the slides, and Dan will present some other of the slides, and there's no particular reason behind chosen order of the slides. With that said, let me begin. Okay, so I'll begin with an old theorem of Albert-Fatih from the 1970s. So let's consider the group consisting of all compactly supported volume-preserving homeomorphisms of the n-dimensional ball, or the n-dimensional disk. So that's what the notation here stands for. So the C, the little c you see in subscript stands for compact support, so meaning we're looking at those homeomorphisms which are identity near the boundary. And the omega stands for, say, a smooth volume form on the manifold, or on the n-dimensional ball. So in the 70s, Fatih was interested in the algebraic structure of this group, and among other results, he proved the following theorem. He showed that this group, so the group of compactly supported volume-preserving homeomorphisms of the n-dimensional ball, is simple when the dimension is at least 3. Okay, so simple meaning it has no non-trivial proper normal subgroups. Now, as you could see, Fatih's theorem leaves out two cases, n equals 2 and n equals 1. Now, when n is 1, the group is just a trivial group. There's nothing to check. And so the remaining case is that of n equals 2. So in that case, the question becomes, is the group of compactly supported area-preserving homeomorphisms of the 2-disk a simple group or not? So that's a question that he raised in his paper from the, I believe it's from the late 70s or maybe 1980. And over the years, this question attracted quite a bit of attention in dynamics, topology, and later on in the symplectic community. And you know, eventually, within the symplectic community at least, a consensus was formed that, we'll see, the symplectic nature of the question in dimension 2 should force the existence of a proper normal subgroup. Okay, so the answer should be different in dimension 2. And this became known as the simplicity conjecture. Perhaps it should have been named non-simplicity conjecture, but people called it the simplicity conjecture. So the simplicity conjecture says, is the group of it says that the group of compactly supported homeomorphisms of the 2-dimensional disk is not a simple group. Now, one thing I want to point out is that you know, this group of area-preserving homeomorphisms of the disk comes equipped with a natural topology, the C0 topology, or topology of uniform convergence. And so it's a topological group. However, the question this simplicity conjecture question is a purely algebraic question. It has nothing to do with the topology of the group. Because it was already known at the time of Fatih's question that as a topological group, it is simple, meaning it possesses no closed proper normal subgroups. And now, if you think about this topological simplicity of the group, it already kind of gives you a hint as to why the question is tricky. Imagine you want to prove the conjecture. One of the most natural things to prove a group, you know, the natural approach towards proving a group is not simple, is to write a homomorphism out of the group. Now, any naturally constructed homomorphism on a nice topological group like this would likely turn out to be continuous. However, since the group has no closed proper normal subgroups, it admits no continuous homomorphism. A continuous homomorphism would have to be, the kernel of a continuous homomorphism would have to be a closed normal subgroup. It would be the whole thing. And this is part of the reason why this is a difficult question to approach. Okay, so this brings me to the main theorem of today's talk, which is that the simplicity conjecture is not true. So the group of area-preserving homeomorphisms of the disk is not a simple group. So this is, we proved this jointly with Dan Cristofaro-Gardner, who's here, and Vincent Millier in 2020. And this was the paper for which we received the FSA prize here. Okay, so the group is not simple. It must have some proper normal subgroups. And I can give you an example right off the bat. Okay, so it turns out that the commutator subgroup, so the group just formed by taking products of commutators, that's a proper normal subgroup. Okay. It's not obvious that that's a proper normal subgroup, but this turns out to be a consequence of our work. And we'll see later on why this is the case. Let's see, is there anything else? Right, so the proof requires ideas from symplectic topology. And as the first hint, let's see, in dimension 2, a volume form becomes a symplectic form, meaning it's a closed and non-degenerate 2 form. Okay? And that's the first place where the connection to symplectic geometry comes in. You don't really need to know much about symplectic geometry, a little bit, okay? And I'll recall what's needed. So one thing I want to comment on, for those of you who are familiar or have some level of familiarity with symplectic geometry, is that symplectic geometry is a subset of smooth differential topology, so smooth differential geometry. Symplectomorphisms are smooth objects. So when you write the equation describing the symplectomorphism, you're describing conditions on derivative of the map phi. Okay. However, this main theorem of today's talk, it's a statement about homeomorphisms, non-smooth objects. So why is it that symplectic topology, which is inherently a smooth field, able to answer questions about homeomorphisms? Okay, so I just want to say a few things about the philosophy behind what goes into here. So to explain this, I will tell you a little bit of a story that goes back again to the 70s, to the origins of the field of symplectic geometry. So note that if you have a symplectic form, since it's non-degenerate, let's assume the manifold is 2n dimensional, once you raise it to power n, you get a volume form on the manifold. And symplectomorphisms are all volume-preserving diffeomorphisms. They form a subset in there. Now let's consider the following. Let's consider the C0 closure of symplectomorphisms taken inside volume-preserving diffeomorphisms. So that's what I'm denoting by simp bar here. Okay. So a priori, this is a subset in between the two. It sits somewhere, it must include all symplectomorphisms, and it sits somewhere between symplectomorphisms and volume-preserving diffeomorphisms. Now, Gromov was interested in where exactly between the two it sits. And he was working on this again in the 70s. Much of the story goes back to the 70s. And he proved the following famous alternative, which he called the soft versus hard alternative. So he showed one of the following two statements is always true. Either this inclusion is an equality on the left side, so meaning that when you take the closure, you get nothing new. This is what we call the hard or the rigid alternative. Or if this fails to be true, then the other inclusion is an equality. So you get nothing in between. He showed that you either get nothing new, or if you get one new object in this closure, then you get all volume-preserving diffeomorphisms. So you get either the soft or flexible alternative or the hard or rigid alternative. And so he proved this in the 70s and left the world in mystery. And some 10 years or so later, Eliashberg actually resolved the alternative in favor of rigidity. So he showed that it's always, so you never get this flexible alternative. You always end up with the rigid alternative. So this is what's become known as the C0 rigidity theorem of Gromov and Eliashberg. Now, chronologically speaking, this is this is one of the most, the first major theorem, perhaps, in the field of symplectic topology, and it gave birth to what's called modern symplectic topology. And not only that, it gave rise to what's called continuous or C0 symplectic topology, which is a branch of symplectic topology which studies C0 or continuous analogs of smooth symplectic objects. So for example, the most fundamental notion in the field is that of a symplectic homeomorphism. So we say a homeomorphism of our symplectic manifold is symplectic if it can be written as a C0 limit of smooth symplectic morphisms. And the theorem on the previous slide, the Gromov-Ilya-Ashberg theorem, tells you this definition is kind of well defined, because if this limiting object turns out to be smooth, then it's an honest symplectic morphism. Okay. So what are examples of symplectic homeomorphisms? All area-preserving homeomorphisms of surfaces. And so this is where the connection between smooth symplectic topology and area-preserving homeomorphisms comes from, and that's what allows us to bring the tools of symplectic topology, such as various forms of floor homology, to bear on the question of the simplicity conjecture. Okay, so with that said, I'll tell you a little more about Fathi's question. I told you what his question was for the disk, but he actually posed a more general question about all surfaces, and that's what I want to tell you about next. So now let's consider a surface, sigma, equipped with an area form, and we suppose that it has boundary. So it could be the disk or any other surface with boundary. Then there is a very special class of symplectomorphisms called Hamiltonian diffeomorphisms, which are defined as follows, and these play a really important role in our story. So these arise as solutions to Hamilton's famous ODE. So they're defined as follows. You begin with a time-dependent function or a Hamiltonian on your surface. I suppose it vanishes near the boundary. That's just a technical assumption, but it's important. And then you could associate to this a vector field, which is defined via this equation. Once you plug in the vector field in the first component of the form, you're supposed to get back the differential of the function. In local coordinates, so if you're on a disk and the coordinates are x, y, it's given by this, this is the formula for the vector field. This is Hamilton's ODE. Now you take the flow of this vector field, it generates an isotopy, and that's what we call a Hamiltonian isotopy, and the set of all diffeomorphisms which arise in this way are called Hamiltonian diffeomorphisms. Okay? And these all turn out to be symplectic. So in particular, in the case of surfaces, they sit inside area-preserving diffeomorphisms of the surface, particularly inside the identity component there. If you take the case of the disk, which we already discussed, the Hamiltonian diffeomorphisms of the disk are exactly the compactly supported area-preserving diffeomorphisms of the disk. Now, there's a notion of a Hamiltonian homeomorphism. So let's consider an area-preserving homeomorphism of any surface, which with compact support, so meaning its identity near the boundary. Then I say a homeomorphism is Hamiltonian if it can be written as a limit of Hamiltonian diffeomorphisms, the C0 limit. And we denote the set of all such things by Ham bar. So these are Hamiltonian homeomorphisms of the surface. And this sit inside area-preserving homeomorphisms of the surface. Usually they're a proper subset. In the case of the disk, it turns out to be all area-preserving homeomorphisms of the disk. And now Fathi actually asked this more general question. Is this group of Hamiltonian homeomorphisms of any surface a simple group or not? Okay, so it clearly generalizes the question about the disk. And to give you some context for why he asked this question, maybe I'll recall a little bit on the next slide the series of works he did that led him to this question. Okay? So now we go back to Fathi's work from the 70s again. So let's consider M an arbitrary manifold equipped with a volume form, and we consider the identity component inside the group of volume-preserving homeomorphisms of the manifold. And he was interested in knowing whether this is a simple group or not. So the reason we consider the identity component, by the way, is that the identity component is a normal subgroup inside the larger subgroup of all homeomorphisms. So the question is really interesting here. And he was interested in this question, and he managed to actually largely answer this question, and the answer can be summarized as follows. It will be a 3-line summary of a long paper. This is what he proved. He constructed a homomorphism, which he called the mass flow homomorphism. The symplectic geometers should think of this as something very similar to flux, out of the group. Okay? So what's important is that we have a homomorphism out of the group. It takes values in some quotient of H1. This subgroup you're modeling out by gamma is not too important. You could just ignore it. I just put it there to be correct. So we have a homomorphism out of the group. And okay, so since you have a homomorphism, you could take its kernel, and whenever the kernel is proper, it gives you a proper normal subgroup. So it answers the question. And actually, he showed that the homomorphism is actually non-trivial as soon as each one of the manifold is non-trivial. So this largely answers the question. Sorry, this is a theorem he proved. He showed that the obstruction to the group being simple is whether this kernel is trivial or not, whether the kernel is the whole thing or not. And then he showed that the kernel itself is always a simple group. The kernel of this mass flow homomorphism is always simple in dimensions greater than or equal to 3. So of course, again, as before, this raises the question of what happens. So as a corollary of this, before I go on, you see that the case of, he gets the case of volume, proves that volume-preserving homeomorphisms of the n-dimensional disk for n greater than or equal to 3 is simple, because there the kernel is everything. So then the question remains as to what happens in dimension 2. Okay? And so here's a fact that can be proven. This brings us to the next portion of the talk. In dimension 2, the kernel of this famous homomorphism is exactly these Hamiltonian homeomorphisms of the surface. So that's what led Fatih to his question. I think at this point I'll hand over to Dan, who will continue for the next little while. Do you want this, or?
I'll just use this.
Okay.
Okay, thanks a lot. Yeah, so just to recap a little bit where we are, in higher dimensions, Fatih had shown that the kernel of this mass flow homomorphism is always simple. Then in the case of surfaces, in 2020, our FSA paper showed that for a disk, the analog of this is false. The kernel of mass flow is not simple. But now we're going to explain to you some later work generalizing this to arbitrary surfaces. Review. So here's the theorem. In addition to the three of us, we proved this jointly with Chuck-Yu and Ivan, which says that, yeah, in fact, for any surface, the kernel of the mass flow homomorphism, or as Sobhan was saying, in other words, the Hamiltonian homeomorphism group is not simple. So again, it contrasts the situation in higher dimensions. So let me give a few remarks about this. So our FSA paper used an approach using periodic floor homology. To keep things simple, we don't want to go too much into this, but the periodic floor homology is quite closely connected to dynamics, and there's value in using periodic floor homology beyond just questions about algebraic surfaces of algebraic structures of homeomorphism. Like later work built on this to prove closing lemmas and things like this. However, for the unified treatment we want to explain to you today, it's good to talk about an approach using Lagrangian floor homology that we're now going to explain. And our approach has a long history that is inspired by a number of authors, the main ones being Ajvath and Szabo, Chuck-Yu and Ivan, and also Polterovich and Shulkin, who used this Lagrangian floor homology approach to reprove our theorem. Yeah, just stop me if you have any questions about how this all fits together as well. Oh, and also actually, another interesting proof was given by Oliver Ettmeyer of our theorem, which doesn't use floor homology at all. Okay, well, before explaining the proof, we just wanted to give you a little bit more context for how to think about these questions and why you might care about them. So, first of all, just to give you some sense of history, the question about these algebraic structures of homeomorphism proofs really go back to Ulam, who asked the following question in his Scottish book, which is essentially about whether essentially amounts to whether the identity component in the group of homeomorphisms of the n-sphere is simple. And I guess more generally, there's a philosophy that the algebraic structure of some transformation group like this should encode essential features of the underlying geometry. So in Ulam's question, this is the case where there's no underlying geometric structure. We're just talking about homeomorphisms. But it's instructive to compare with what goes on for other kinds of transformation. So historically what happened is that for the circle and the two-sphere, this was answered by the 40s. And then later work generalized this to any manifold. And I think it's, interesting to see the general picture that one has for these kind of questions. What you see here is that if I'm just talking about homeomorphisms or diffeomorphisms, I'm not fixing some extra structure. The groups just tend to be simple groups. So then you can ask, what if I add some additional geometric structure to the problem? What do I find? And okay, well then it's like the kind of thing that Sobhan was saying earlier in his talk. Here's some key examples. Well, Sobhan already talked about homeomorphisms, preserving a volume measurement. Here's diffeomorphisms, preserving a volume form. Some plectomorphisms. Anyways, what one tends to find is that the groups are not necessarily simple when one adds a geometric structure. However, they tend to admit natural homomorphisms. Sobhan described, at least impressionistically, this flux homomorphism and the mass flow homomorphism. Anyway, so if you have a homomorphism, a non-trivial homomorphism, you won't be simple, but then what you can hope is that your kernel is simple. And that's what one tends to find. And it's worth emphasizing that because even still, that does not appear to be our current understanding of the area-preserving homeomorphism group in dimension 2. So it's quite a new phenomenon, what we find. So just to expand further on what I was saying, in our case, so that's the case of Ham bar, in other words, it's the kernel of mass flow in dimension 2, there's not necessarily a natural homomorphism, though in the final part of our talk we want to expand on this a little bit. So we're being kind of purposely cagey here in saying that there's seemingly no natural homomorphism. But anyways, as Sobhan was saying, the normal subgroup that we're trying to pick out is necessarily topologically dense. So it has to be a strange homomorphism if you're gonna get something out of it. And so it certainly looks a little bit different. And we still don't really have a good picture where eventually you get to something which we are sure has to be simple and is described by a natural homomorphism of this nature. Okay. So with that out of the way, we now want to tell you a little bit more about how you actually prove things, at least in an impressionistic sense, about these groups. So in particular, we're going to explain, at least in a high-level sense, why these surface transformation groups in the area preserving category are not simple. And just for simplicity, it's good to stick to just the case of a disk. Although everything I say here admits a generalization to an arbitrary compact. So the first thing to wrap your head around is what happens in the smooth case. So in the smooth case, there is a natural homomorphism. It's a so-called Calabi homomorphism. And later we'll elaborate further that Banyaga showed that the kernel of the Calabi homomorphism is simple. So in the smooth case, it's like the kind of story I was telling a couple of slides ago, but it's very good to review this. So what is this Calabi homomorphism? Well, in some sense, it measures the average rotation of your diffeomorphism. So again, imagine D is a two-dimensional disk. We're looking at diffeomorphisms that are the identity near the boundary, area preserving. You can just imagine your area form is the standard one. And we want to define some kind of average rotation. Well, it turns out there's a very nice way to do this. So what you can do is if you have such a diffeomorphism, it turns out by basic symplectic topology that you can always write that as the time one flow of a Hamiltonian. And because it's compactly supported, you can normalize the Hamiltonian is 0 near the boundary. And then you can just integrate the Hamiltonian and you get a number. And really the amazing fact, the really cool thing is that it doesn't depend on the choice of Hamiltonian. And you can see that the normalization condition is important for that, because otherwise you could just add a constant to your Hamiltonian, it would change the integral, but since we're normalizing that it's 0 near the boundary, at least we can't do that. Now, in general, there will be multiple Hamiltonians generating the exact same time one map. But the cool thing is that that doesn't affect the value of this. And once you know that this actually is well defined, it's not so hard to show that it's a homomorphism. And some further thinking tells you that it's a reasonable description of the average rotation of the map. So there you go. There's your homomorphism in the smooth case. And as I said, Banyaga showed that its kernel is simple. And right, so the starting point for all of the works that we mentioned is really just trying to think about to what extent this makes sense for homeomorphisms. I mean, if you have an arbitrary homeomorphism, you can no longer write it as the time one flow of a Hamiltonian, so you have to think a lot about it. Okay, so, well, there is a natural thing to try to do, which is to just extend Calabi in some kind of natural sense. It's not so hard to see that the diffeomorphism group is dense in the C0 topology. We have a homomorphism on diff, so you could just try to extend it by C0 continuity to homeo. And that was a question that Fatih asked in his original paper. Gies also asked the question in his 2006 ICM address. So if you could do that, then the group is not simple. What's the problem? Well, the naive way to do that would be to extend it by continuity. But the problem is that this homomorphism is not continuous. And there's a simple example, I believe, due to Sobhan. Do you find this?
No, I don't. Probably not.
Okay.
Yeah.
Well,
there's probably no one before me.
There's a simple example for why this is not zero continuous. I guess that has been known to man for years, known to mankind for years. Okay, so remember, the Calabi invariant is just the integral of the Hamiltonian. So you could imagine taking a Hamiltonian with total mass 1 that is getting more and more concentrated along the origin. So whatever the flow is, it's not going to do anything outside of the support of the Hamiltonian. So in particular, the time one map of the Hamiltonian flow for this is going to converge in C0 to the identity. On the other hand, just by definition, the Calabi invariant of each one of these phi sub n's is 1, but the Calabi invariant of the identity is 0. So therefore, we see that the Calabi invariant is not 0. Are there any questions about that or anything? Okay, so given that it's not C0 continuous, this naive idea of just trying to extend it in some topological way just does not work. So nevertheless, we were later able to show that it does extend to the full group. And then later at the final part of the talk, Sobhan will talk about some kind of universal extensions. And we want to explain a little bit how this works. And floor theory plays a key role in our arguments. Just to say a couple of remarks about this. To put this in some context, of course, once you have an extension, it immediately answers the simplicity question because it implies that this is not simple. And it singles out some particular normal subgroups for you. For example, we can look at the kernel of this. As Sobhan was saying, we can look at the commutator subgroup. An interesting question is exactly what these have to do with each other. Maybe you could imagine that this commutator subgroup is going to be the kernel of this. That's what happens in Banyaga's case, for example. But we don't have a very good understanding of how to characterize the commutator subgroup in terms of a homomorphism stuff. As we're saying, the commutator subgroup is certainly part of the kernel of this, but we don't have a good understanding. Another remark is here we're talking about the case of the disk, but for general surfaces, our work was generalized by Mack and Treefan, 2023. Yeah, so that's what I want to explain to you. How does this work? At least, I mean, actually our papers are quite long and technical, whereas this is going to be quite short and not technical. But at least I hope you get sort of the main points. Okay, so here are the main points. I mean, we literally enumerated them for you. So you imagine we have this Calabi homomorphism. We want to try to extend it, but it's not C0 continuous. Kind of a strange thing. Okay, so, the first part is appeal to Floer homology. So, for time reasons, we don't have much that we're going to say right now about Floer theory, although we do have some bonus slides if we have time at the end. Floer theory is a whole package, and you can use it in particular to define what are called spectral invariants. I mean, if you're really visiting this from another field, very roughly speaking, you can think of your favorite kind of spectrum, like perhaps like the eigenvalue spectrum of a Laplace operator on a bounded domain, and there's a lot of similarities, actually, to the eigenvalue spectrum. It's just our spectral numbers, so these are just real numbers, and they're defined by Floer theory rather than by something like an eigenvalue of a Laplace. So use some Floer theory to get a sequence of spectral numbers. Again, if you're really not from the field, maybe think of these as something like eigenvalues of Laplace. There's a whole sequence of them. Okay. Now, remember that we actually want a homomorphism. That's what you want if you want to show that something is not simple. Unfortunately, these spectral invariants won't be homomorphisms. I mean, maybe it's not even unfortunate, because as Sobhan was explaining, you're trying to do something quite subtle. You're trying to capture a dense subgroup, and so as you'll see when I put all the properties, it would actually be rather unrealistic if these really were homomorphisms. Anyways, they won't be homomorphisms. But they're actually almost as good. They're what are called quasimorphisms. So what's a quasimorphism? Well, you can imagine that if these were a homomorphism, if I evaluated them on the product of two elements, it would just break as the sum, and in particular, this would just be 0. So it's not 0, but it's almost 0. It has a defect depending on n, and in fact, the defect is going to 0. So we have these spectral invariants. They're quasimorphisms. What else? Well, they satisfy the so-called while law. This was one reason I stated things in a rather funny way in terms of the Laplace eigenvalue spectrum, because the Laplace spectrum famously satisfies a while law due to while, where one can recover the volume, say, of a bounded domain in Rn from its Laplace eigenvalue spectrum. Here, what one finds is one can recover the Calabi invariant from these Lagrangian Floer theory spectral invariants. So we call this the while law. And it just says that the limit of these quasimorphisms recovers Calabi. Okay, so then things are hopefully looking pretty good for you. In other words, look at what we wanted to do. We wanted to extend this thing Calabi. We have it as the limit of some things. Those things are quasimorphisms. It's looking pretty good. There's maybe one more key point, which is that, remember, we actually wanted to study the homeomorphism group. So far, we've just defined things on the diffeomorphism group, but the amazing thing about these spectral invariants, another thing you get from the Floer theory package pretty naturally, or at least somewhat naturally, and that connects to what Sobhan was saying about continuous symplectic geometry, the wonderful thing is the spectral invariants actually are C0 continuous, and they extend to the homeomorphism. So now I would say it really looks good. We have numbers on the homeomorphisms. So these do make sense for homeomorphisms. They even extend by continuity. They're almost homomorphisms, and they recover the Calabi invariant in the limit. Okay, so then you just have to put this together to get some kind of extension. Okay, so now actually there's some interesting logic, by which I mean sort of, I'll say at the end, but let's set that aside for a moment and just do it. So let's try to write down a homomorphism from these quasimorphisms. What's a nice way to do this? Okay, well, you can look at this space, script A. I think the logicians like to call this R to the n mod C0. R to the n where n is the natural numbers. So this is just the set of all sequences modulo those sequences that converge to 0. This is going to be the natural repository for our homomorphism. Remember, we're trying to define something like the Calabi invariant of a homomorphism. So we want to take a repository in this script A. So just to say again what this means, in script A, two sequences are equivalent if and only if their limit is 0. So for example, if your sequence actually converges to a limit, then it's equivalent to the constant sequence. All right, so now we're going to define our homomorphism. So it's quite natural the way I've set it up. We just take our area-preserving homeomorphism to its sequence of spectral invariants. Again, stop me if you have any questions. And okay, the way I've set it up, it's even an exercise you could assign to your undergraduate algebra students that all this actually works the way we say it does. But it's instructive to go through it. So first I claim that this is a homomorphism. Remember that each one of the spectral invariants are just quasimorphisms. They're not homomorphisms, but the reason I've quoted it out by this funny equivalence relation is to make this work. So why is this a homomorphism? Well, again, its defect from being a homomorphism goes to 0 with n, and we're exactly modding out by that equivalence relation. It's homomorphism. Okay, now remember, if you want to show that something is simple, it's not quite enough to have it's not simple. It's not quite enough to have a homomorphism on it. You have to have a non-trivial homomorphism. So how do I know that this isn't just the 0 homomorphism? Well, that's where the while law comes in. So if I happen to evaluate it on diff, then, just like we were saying that, remember, if an converges to a, then in script a, an is just equivalent to the constant sequence. So on diff, this thing is just equivalent to the Calabi invariant. So therefore, it can't be 0. So there you see, the while law guarantees non-triviality. The quasimorphism property guarantees that it's a homomorphism. The continuity property guarantees that it actually makes sense. So that's how it all fits together. Then you have to just prove that these spectral invariants actually satisfy all these properties. You can read our various papers for that. Okay, so just a couple more things to say about this. Okay, so as I remember, Fatih's actual question was whether the Calabi homomorphism extended to R. Remember, the original Calabi homomorphism is taking values in the real numbers. And so one thing you might want to try to do is extend it to something still taking values in the real numbers. Now, before I get into that, I want to emphasize that if you just want to prove non-simplicity, this kind of thing is irrelevant, because having a homomorphism to script A is perfectly fine if you just want to find a non-trivial normal sum. But maybe you actually want a real valued extension of Calabi. You can do it if you use Zorn's lemma. This is where I said there's some interesting logic here. If you use Zorn's lemma, you can find basically just a section of the diagonal embedding, and you can just project the section. But this is a little bit weird because this is not done in a canonical way. This actually tells you have infinitely many extensions of Calabi. It's not a very canonical thing. So you could do it, but in fact, actually, after the fact, it turns out that if you want an extension to R, you more or less have to do something like this. Because as Sobhan was saying, you should not be able to find continuous homomorphisms. And in fact, there are models of ZFC where one doesn't assume the axiom of choice, where every homomorphism between homeo and R would automatically have to be continuous. There's something called an automatic continuity property. And so evidently these extensions don't exist in those models of ZFC. So the upshot is that you have to do something like this if you actually want an extension to R. But why you would want an extension to R, I don't know. I don't really like extensions to R. But all right. So with all that said, now I'm going to turn it over again to Sobhan, who's going to talk about a universal extension, which again won't be taking values in R.
Great, thanks, Dan. Okay, so this last portion of the talk, so this is, we'll talk about an extension of Calabi, which won't use the axiom of choice, and it will satisfy some universality property. So this is what I'm about to tell you all from this point onwards is a joint work between me and Oliver Ettmeyer, and hopefully it will appear in the archive rather soon. Okay, so let's see why we started thinking about this universal extension of Calabi. So suppose you have two surfaces, now sigma 1 and sigma 2, say. They're both open and connected surfaces with area forms. And let's say you have an embedding of one surface into the other. Now, this induces an embedding of the group of Hamiltonian diffeomorphism of sigma 1 into sigma 2. You just view the Hamiltonian diffeomorphisms of sigma 1 as sitting inside sigma 2. It's a very natural embedding. It's just via the push-forward argument, via the push-forward. Now, it turns out, and this is really easy to see, the Calabi homomorphism satisfies this naturality property. Meaning, if I view the diffeomorphism as a Hamiltonian, given diffeomorphism, if I view it as a Hamiltonian diffeomorphism of sigma 1 versus a Hamiltonian diffeomorphism of sigma 2, it has the same Calabi invariant, because you just take one Hamiltonian that generates and you integrate that Hamiltonian. That number is independent of the surface, as long as the embeddings are area preserving. And it's this naturality property that kind of put us on a search towards this. Now, there's another fact that in the smooth setting that is kind of quite classical and well known, and it's nice to have, is that this embedding, the map induced on the Hamiltonian diffeomorphism groups by the embedding actually induces an isomorphism once you pass through the abelianization. Okay? So this Ham-Ab stands for the abelianization of the group of Hamiltonian diffeomorphisms. Now, in fact, it's well known from Baniaga's work that the abelianization of Ham is just a real line. So this embedding just gives you an isomorphism between. If you could set up an explicit choice of an isomorphism between abelianization of Ham and the real line is given actually is induced by the Calabi homomorphism. And so if you take that as your identification of abelianization of Ham with R, then this actually just becomes an identity. Okay. And the question Oliver and I were looking at is how much of this extends to the C0 setting. Okay. So keep in mind the extension of, we were particularly interested in the naturality property, but keep in mind that the extension of Calabi that Dan just described was constructed via the axiom of choice. And so there is just no reason why it would satisfy a property like this, because it's just a bit ad hoc. It depended on the choice of the surface, and the spectral invariants actually a priori depend on the choice of the surface too. So there is no reason to think that it satisfies that naturality property. So here's the question then we are trying to answer. So now you take two surfaces as before, they're open surfaces, you take in topological area preserving embedding of one into the other. And this induces, once again, a homomorphism at the level of, between the Hamiltonian homomorphism groups. Just inclusion of one group into the other. And this gives you in turn a homomorphism induced at the level of abelianizations. Okay? So, up until our work on the simplicity conjecture, talking about this homomorphism was a bit meaningless because we did not even know if these groups were non-trivial. So at this point, we do know these groups are non-trivial. Right? And what we proved recently, jointly with Oliver Ettmeyer, is that this homomorphism, like in the smooth setting, turns out to be an isomorphism. Okay? So once you pass through the abelianization, this inclusion of one surface into the other induces an isomorphism between between the two groups. And moreover, this isomorphism is actually unique. It doesn't even depend. It's a canonical isomorphism once you pass the abelianization. It doesn't depend on the choice of embedding. So if you take two different embeddings, you get the exact same isomorphism. So now, this allows me to make sense of this. I will define this curly R, which is now going to be the repository for this universal extension of the Calabi invariant, to be just the abelianization of Hamiltonian homeomorphisms of a disk, or area-preserving homeomorphisms of the disk. And this curly R, by this theorem, it doesn't depend on the choice of the surface, actually. I mean, I could have taken it to be the abelianization of any surface, of Hamiltonian homeomorphisms of any surface. Okay? Okay, so I've got this group R, curly R. Let's take a look at it. There's a natural embedding of smooth Hamiltonian diffeomorphisms into Hamiltonian homeomorphisms. which in turn induces an embedding at the level of abyllinizations, induces a map at the level of abyllinizations. Now, this mapping actually turns out to be injective. Injective, but not surjective. The important point is that it's injective. The fact that it's injective is, again, it's a non-trivial fact that it's injective, because the fact that this we already know is the real line. So this is telling us the real line injects into the abylinization of our group, and in particular tells you that that group is non-simple. And for that, you need what Dan described just a few minutes ago. So we've got, this line is explaining why the real line, this abylinization of smooth guys is the real line. So we can view the real line as sitting inside this curly R, abylinization of Hamiltonian homeomorphisms of this. Okay? And now we have a commutative diagram that looks like this. I mean, this right-hand side is just labeled for these groups, so just focus on the left-hand side. And we have a commutative diagram like this. The vertical arrows are all injections. Just couldn't quite get the LaTeX to put a hook here. So these are all injections. I mean, this one is clear because Hamiltonian diffeomorphism inject into Hamiltonian homeomorphisms. The fact that this abylinization injects into the abylinization of Hamiltonian homeomorphisms, that's a consequence of the work with Dan and Chokchu and Ivan and Vincent. And so this bottom row here is actually the Calabi homomorphism, the smooth Calabi homomorphism. Therefore, you could think of the top row. So let me go back here. So we've got this picture here. So the mapping that starts from Ham and goes through a real line, that's the Calabi homomorphism, and you've got this commutative diagram. Therefore, you could think of the top row as some sort of a natural homomorphism, a kind of a universal extension of Calabi. We call it the universal extension of Calabi, and I'll say on the next line why it's a universal extension of Calabi. It is certainly an extension of Calabi because it just sits inside this diagram. Okay, so why do I call it the universal extension of Calabi? Because it has the following properties. So it satisfies that naturality property that I described earlier. The fact that it satisfies this naturality property, well, comes partially because this embedding of a surface into another surface is a natural mapping. Also from the theorem that said this induces an isomorphism at the level of abyllinizations. And it's also a universal extension in the following sense. So imagine that you have an extension of a billion group. So that's A, and the real line sits somehow in there. So it extends the real line. And suppose you've constructed a system of extensions of the Calabi invariant, which takes values in this abelian group A. Okay, so I'm assuming that I have one extension for every surface. Now, if these extensions satisfy this naturality property above, then they must all come from this universal extension. So meaning you can find a group homomorphism from this curly R to your group A, and that extension that takes values in A comes from that composing with that group homomorphism. So this is somehow kind of a universal extension. This is what we call the universal extension of Calabi. Okay, and so in particular, the extensions we had, which Dan described, which took values in the real line, they can be obtained in this way by just picking a homomorphism from this curly R to the real line. Okay, and I think that brings me to the end of the talk. How am I doing with time? I hope I haven't gone over time. Okay, good. 2 minutes short. Oh, great. Yes.
What Lagrangians are you using?
So we could try. We have bonus slides. Yeah, we'll show you the Lagrangians.
You draw them, right? Go to the bonus. You have
Okay, so this bonus slides.
we could go ahead and just show the picture.
I'll show you the pictures. Actually, not this part. This was the intuitive idea behind it. But so here's the Lagrangian. We take a collection of curves. So it's a Lagrangian that sits inside the sphere, and you should imagine the disk sitting inside the sphere. So it's Lagrangian floor homology for these curves on the sphere, but not exactly on the sphere. So you take a collection of curves, so the boundaries of these disks, which satisfy these conditions. They all have the same area, and there's n of them, and the complement has the same area. Now, you could build a Lagrangian torus from this. What you could do is take so I'll describe what this is. You could take the product of these tori, these Lagrangian circles. That gives you a Lagrangian torus inside S2 to the power n. Now that Lagrangian torus has trivial floor homology. But it's products of the sphere. And you have the action of the symmetric group on this. So you could quotient out by the symmetric group. And since the component, this induces for you a Lagrangian torus in the n-fold symmetric product of the sphere. And it sits outside the diagonal. Okay, this describes it. So this is the Lagrangian. You take its products, you mod out by the action of the permutation group, and you get a Lagrangian torus sitting inside n-fold symmetric product of S2. And now this n-fold symmetric product of S2, it can be identified with CPN. A priori, it's actually an orbifold, something you like, but actually, since it's two-dimensional, you could smooth out the orbifold, and note that the Lagrangian is outside the diagonal, so you could smooth it out and get a smooth Lagrangian that sits inside CPN, and it actually turns out to be to have the same disk potential as the Clifford torus. It's actually the Clifford torus. So then what you end up doing is Lagrangian floor homology. Now the map phi from the sphere induces a map on the whole picture. So you end up doing Lagrangian floor homology between this torus and its image under the map induced on CPN by the area preserving map of the sphere.
So, earlier I made a brief remark about how our original proof used periodic floor homology. Periodic floor homology is something like embedded contact homology, which is isomorphic to Haggard floor homology. And this is something like the Haggard floor version of what we were doing with periodic floor homology.
Yeah, this is quite similar to Haggard, in some variation of Haggard floor homology.
That's why we edited Ajra stuff.
Yeah. I mean, the paper with Chukwu and Ivan is called, with Chukwu Mark and Ivan Smith, yeah. It's called quantitative Haggard floor homology.
So together like a bunch of disks. You apply phi to them against a bunch of other disks.
Yeah.
So an intersection points like a two.
Yes. Yes.
And you can sort of see that they're spreading out and seeing the Calabi variant. You can kind of see the Y law this way. The Calabi variant is like the integral, and in some sense they're behaving like the Riemann sum.
Yeah, the fact that these are, as you see, as n increases, these disks kind of fill up space. So you could probe like small area regions of the sphere. And that's kind of the geometric idea behind why you recover the average of a given Hamiltonian.
Is there any other question?
You didn't define the CN.
No, we didn't.
Maybe it's there.
Is there a bonus slide here for this?
More bonus. This is a proof of the Calabi variant. The CNs.
Well, they're spectral invariants.
Yeah, it's a long story.
Yeah. How are they ordered?
Well, that's good. Yeah, what's n? N is the number of. Sorry, we're in full.
No, go ahead.
N is the number of links here. So for each n, you have a Lagrangian torus, and n, you have a non-zero Lagrangian floor homology group, and there's a whole package of Lagrangian spectral invariants. But in particular, this has a fundamental class, and you can just evaluate the Lagrangian spectral invariant on the fundamental class. More or less, that's.
Okay.
Right. Yeah. So this floor homology groups they carry a filtration. A real value. You could put a T here, and for every T in R, there is a floor homology group. And as you increase T from minus infinity to infinity, you start seeing certain homology classes. At some point, you see the fundamental class of the torus in there. That's the value of this spectral invariant. Josh.
But is there some simple geometric picture for what the spectral invariant is? It's like the area of some interesting picture in that disk.
No, I can't identify.
Some kind of chord. Hamiltonian chord.
Right, the generators of the complex are going to be what Mark just described. There's some chords that go between the circles. The process just picks out one particular chord which is homologically significant, and it picks out that action. Now, we can't draw it. In your story, there's a really nice picture of the spectral invariant. Here, we can't pick it out. Now, what turns out...
It's for an arbitrary band. So, you know, in our original paper on periodic floor homology, we actually only computed with twist maps. And then if you have a twist map, you can, at least in periodic floor homology, more or less see which periodic orbits are carrying the spectral invariant. And it's a beautiful story with lattice models and things like that. But if you just have an arbitrary area preserving diffeomorphism, I think it's hopeless.
So, yeah, for an arbitrary, but for special examples, it's possible. Maybe to connect to your work, that maybe you'll talk about on Friday, you're looking at a very special class of maps. That's why you get really nice pictures where you could see the geometric picture that connects to the spectrum. Here, it's not. So, yeah. What allows us to prove the Wien law is that these satisfy a certain set of axioms, these spectral invariants, and then you put those axioms together and somehow this implies the Wien law. But the geometric idea why the Wien law is satisfied, because when you have many, many, many circles, the spectral invariant looks more and more like a Riemann sum.
That's what I'm saying. The Hamiltonian is constant on the circle. If you happen to have a Hamiltonian that's constant on the circle, then it's just the value of the Hamiltonian. It's what the number is. That's very helpful.
Great.
More question? If no more question, we thank the speaker again.
Oh yeah, good job.
Then we resume in 50 minutes.